Okay, let's go ahead now and start to take a look at the example problems for today's series of lectures. Okay, the first two problems are specifically concerned with the lens maker's equation. So let's begin to take a look at the first of those two examples. Go ahead and access those examples and write down the first example now in your notes. Okay, the lens maker's equation is basically the right-hand side of the equation, if you will. And that's this expression here. Okay, now, hopefully you took a look at my lens maker's equation demonstration video. If you haven't done so, please do so now. But in that video, I demonstrate that it doesn't matter in which direction you look through the lens. You always see the same sort of image. Okay, the reason for that is because there are two foci associated with each lens, one on either side of the lens, and the focal length is the same value for both sides. We'll illustrate that here by using the lens maker's equation. Okay, now with the first example, we have a lens that is shaped like so. Like this. And then we have two radii of curvature of 10 and 20 centimeters. So which surface is which? Well, this sphere right here on the left is smaller than this sphere here on the right-hand side. So then therefore this sphere here on the left has the smaller radius of curvature, 10 centimeters. And this one here on the right has the larger radius of curvature, 20 centimeters. And now specifically, let's say that we hold the lens like this and then look at light that's coming from the other side of the lens like so. And the index of refraction here is 1.5. Okay, so if the light is coming from here, this now is the first surface, R1, and this right here is the second surface, R2. But when I use the lens maker's equation here, I have to get the sign convention correct. So take a look at the first surface. The center of this sphere is over here. It's on the opposite side of this surface from where the light is coming from. Therefore, from the sign convention, this is a positive number. However, the center of this sphere is over here on the left somewhere. It's on the same side of this surface from where the light is coming from, so then therefore from the sign convention, this right here is a negative number. And now what we do is we just plug everything in. That's the hardest part of doing this process, by the way, is just getting the sign convention correct. After that, you just plug in. So we have here 1 over the focal length, and this then equals 1.5 minus 1. And now I have here 1 over R1, so 1 over 10. And then minus then 1 over R2, so negative 1 over 20. And notice that inside of these big parentheses here, I end up with a positive number. So let me go ahead and do the math here for us. Okay, in the big parentheses, I actually have here, let's see, 2/20 plus 1/20 when you cancel out the negative signs, for a total here of 3/20, so 3 over 20. And then multiply that here by a half out in front. And then don't forget to take the reciprocal here at the last step to get the focal length. Okay, when I calculate the focal length here, it ends up being a positive 13.3 centimeters. Positive focal length indicates that this lens is converging. But now let me go ahead and resolve the problem, but in this case, let's assume that the light is coming from the other side. In other words, let me redraw the diagram. Like so. But now let's say that we're holding on to the lens like this and we're looking at light that's coming from over there. So now the light is coming from this direction. So then therefore this here, the 20 centimeter curvature, well that becomes the first surface now. And then right over here, the 10 centimeter curvature, that becomes the second surface. That then is the radius of 10 centimeters. But now we have to get the sign convention correct. So take a look at the first surface right here. The center of this sphere is over here on the left. It's on the opposite side of this surface from where the light is coming from. Therefore, it's a positive number for that reason. Okay, and then the center of this sphere is over here on the right-hand side. It's on the same side of this surface from where the light is coming from. So in the sign convention, this then makes that a negative number. So the radii of curvature here, they switch identities from R1 and R2 above, but you'll also notice that they switch signs. Watch what happens now when I plug everything into the lens maker's equation. So 1 over the focal length equals then 1.5 minus 1, and then I have here 1 over R1 minus 1 over R2. Like so, I know that's a little bit messy, but take a look at this expression here, and you'll notice it's exactly the same thing as the equation above. So then therefore, if we calculate the focal length here, it ends up being the same value, positive 13.3 centimeters. So this then means that there are 2 foci on either side of the lens, and the distance that each focus is from the lens is the same value. This also explains why when you take the lens and you flip it around and look at it in the opposite orientation, you always see the same image. For those of you that are wearing glasses, this is difficult to do with contact lenses, but for those of you that are wearing glasses, you can test this for yourself in the following way. Take your glasses and flip them around, like so. And then place the lenses on your nose at the same distance from your eyes as they normally would be when you were wearing your glasses, and then look through the lenses. When you do, it doesn't matter which way you do look through the lenses, you see the same image. Okay, let's take a look at the second example. The second example is just an example of the same sort of process, but in this case with a diverging lens. Okay, so let me go ahead and erase the board here and then draw this situation for this diverging lens. Okay, once again, of course, we're going to be applying here the lens maker's equation. Okay, so now this lens is shaped in the following way. I'm going to kind of exaggerate it here on the diagram for clarity. Like so. And once again, we'll assume that the light initially is coming in this direction. So this right here is then the radius of curvature R1. Okay, this is the smaller sphere than this one is. So this right here is the radius of curvature of 10 centimeters. This right here is the second surface, that's the bigger sphere, so that's the radius of curvature of 20 centimeters. But now we've got to get the sign convention correct. So for the first surface here, the center of this sphere is over here on the left-hand side. It's on the same side of this surface as where the light is coming from, therefore it's a negative number for that reason. And then for this sphere, the center of this sphere is over here on the right-hand side. Therefore, it's on the opposite side of the surface from where the light is coming from. From the sign convention, this then makes this a positive number. And now we just plug everything into the lens maker's equation. So 1 over the focal length equals then 1.5 minus 1. And now here in parentheses, I have 1 over R1, and then minus 1 over R2. Like so. And then notice here in the big parentheses that we're going to end up with a negative number. So the focal length then of this lens, a diverging lens, is negative for that reason. Okay, let me go ahead and do the math. Let's see, this right here is negative 2/20 minus 1/20 for negative 3/20. Negative 3/20, there we go. Multiply that then by a half. And then lastly, take the reciprocal here to get the focal length. Okay, and when I do, it ends up being negative 13.3 centimeters. So the negative focal length here indicates that it's a diverging lens. Okay, now do the problem backwards. That is, I'm going to draw the lens the exact same way as I did before, but now we'll assume that the light is coming from this direction, like so. So this right here is now the first surface, that's the radius of curvature of 20 centimeters. This right here is the second surface, radius of curvature of 10 centimeters, but now we've got to get the sign convention correct. So for this first surface here, the center of this sphere is over here somewhere. It's on the same side of this surface from where the light is coming from, therefore it's negative for that reason. And then the center of this sphere is over here on the left-hand side. It's on the opposite side of this surface from where the light is coming from. From the sign convention, this is a positive number. So once again, the radii here, they switch identities and they also switch signs. Okay, plugging everything into the lens maker's equation. I now have 1 over R1 minus 1 over R2. Like so. And this expression right here is the exact same thing as the expression above. Therefore, the focal length is the same value, negative 13.3 centimeters, and it's a diverging lens. Once again, this explains why you always see the same image when you look through the lens in either direction. It doesn't matter which way you look through it. And it also explains why there are two foci for each lens. Okay, let me go ahead and pause this here for these two problems. We'll get to the last two problems next.